Chapter 9 is all about gases. And for those of you continuing into Chem 2 in a future semester, we will springboard off this conversation into discussing liquids and solids in their own sections in 10 and 11, including solutions. Okay, but we finish this semester with a discussion of gases. Let's think about air to start. Okay? Now, air clearly isn't an element. Okay? Nobody should be surprised by that fact, right? The AR on the periodic table is for argon, not air. Okay? Where did that idea first come from? Well, with the Greeks, we started by just considering four elements of nature: okay? Air, earth, water, and fire. Okay? We talked about those all the way back in chapter 1. We know they're not elements, okay? But what exactly is air? If you've never pondered that question, right? It wasn't until the 18th century that we determined that the air we breathe is actually a mixture of gases. And maybe you're familiar with that fact, right? Largely nitrogen and then oxygen in the second largest component. Okay. So we're going to use air in this chapter to discuss first pressure, which is one of four key variables we'll be talking about in this chapter: pressure, volume, amount in moles, and temperature. Then in video 2, we'll build to the most important idea from chapter 9, the ideal gas law. Then after that, we'll talk about how that relates to stoichiometry, see chapters 3, 4, and 9 all tie together, and then finish up the chapter by talking about diffusion, kinetic molecular theory, and lastly, non-ideal gas behavior. But most of the chapter will be spent talking about ideal gases, which air can approximate depending on the temperature and the pressure we're working at. So let's think about pressure to start. That's covered in 9.1. The definition of pressure, if you haven't had that in a different course, is force exerted on a given area. So pressure is equal to force over area. P equals F over A. Okay. Gas pressure specifically is a result of the force that's exerted by individual gas molecules that are colliding with the surface of an object. Okay, so if you inflate a balloon or inflate a tire, the pressure that's on the inside results from trillions and trillions, think about Avogadro's number, of gas molecules hitting the surface. That's what's keeping the thing actually inflated. Now, here in America, we usually use PSI for pressure, pounds per square inch, okay? Force per area. Okay? We'll use some different units here in a second, okay? But the key idea from right now, right? The force of each of those collisions is small, right? As you're sitting right now, you have gas molecules that are running into your face, okay? But you don't feel the force of that collision. But we get overall pressure to keep a tire inflated, by example, because of the number of collisions in a short period of time. That's how we get high pressure. It's not any one gas molecule, right? It's all of the gas molecules all at the same time. If you got hit with a ping pong ball, wouldn't really be a big deal, right? You'd be a little more uncomfortable if you were getting hit with a trillion ping pong balls simultaneously. And that's the idea we need to carry forward with pressure. How about the atmospheric pressure that we're actually feeling right now? Okay. Well, that's caused by the weight of the air that's above us, right? Draw a column straight above you, all the way out to space. Okay. The weight of all that air in there is significant. Right? You've got the note here that at sea level, pressure is about the same as an elephant standing on a doormat. Right? But you were born into it. You're accustomed to it. However, if you dive down to the bottom of a swimming pool, for example, you can feel that pressure in your ears because there's a lot more on top of you. Yep. So there we see the definition of pressure again. P equals F over A. Pressure equals force over area. Right? And we see that force is in the numerator. Okay? So pressure is directly proportional to force. And it's inversely proportional to area. So that means that there's two ways to change pressure, right? You change the force or you change the area. If you increase the force, you increase the pressure. If you increase the area, you decrease the pressure. And you can flip those two around as well, right? Decrease the area while maintaining the same force, you increase the pressure. So if we take two examples to illustrate that example, right? The force of an elephant, right, walking around the plains, and the force of an ice skater, the pressure rather, the forces would be different. Right? Thinking about the two different pressures, well, the pressure of the ice skater is actually higher. Right? Even though the elephant is heavier and exhibiting more force, it exerts less pressure, right? Because its feet are so much larger versus the figure skater, which is on that really thin blade. How does this relate to our daily life? Well, how about atmospheric pressure and altitude? Okay. If you've ever baked anything, you've probably seen this before, right? Those instructions for working at high altitude. Right? Well, why do those have different instructions at high altitude? Well, the higher you are in altitude, the less air that's above you, right? Meaning that you're under lower pressure. Okay? So if you're under lower pressure, it's easier for water to boil. For example, it's easier for things to rise when they're baking, which is why you traditionally have to bake them longer. And we don't notice atmospheric pressure changes, right? High pressure systems and low pressure systems, but you do notice vast changes, quick changes in atmospheric pressure. Driving through the mountains, for example, right? Getting on an airplane. Big changes are things you'll notice. Okay. So I alluded to units before. Okay. PSI is what we're accustomed to, but the units we'll be using in chemistry are a little bit different. The SI unit, right, we introduced SI units at the beginning of the semester, is the Pascal, which is equal to a Newton per meter squared. Okay. Now, for us, right, because a Pascal is such a small pressure, right, we don't use pascals, and we don't actually frequently use kilopascals or bars, even though those are all units you can use as well. What we'll be working with in Chapter 9 is the unit of atmospheres, okay, which was originally defined to be the average air pressure in Paris. And that's what we're going to be working with, atmospheres, represented by the symbol ATM for ideal gases. Okay? And any of these other conversions would be given to you. But how do we measure these things? How do I measure atmospheric pressure? How do I work with the unit of ATM, atmosphere? Okay. Well, there's two things I can use, a barometer and a manometer. Let's look at a barometer first. Okay. What a barometer does is measure pressure in terms of a column, the height of a column of liquid mercury. Okay. Notice it's open here at the top. So the more atmospheric pressure that pushes down, the higher the pressure, the higher the column of mercury becomes. Right? And the question that you might be asking is, well, why do I use mercury? Right? Mercury is toxic. Well, if you used water, you'd have to have a pretty big ladder, okay? Because that column would be more than 30 feet high. Mercury is convenient because it's a really viscous, thick liquid. So the height of that column is about 760 millimeters under a typical day that we might experience. Okay, 760 millimeters, that's easy. Okay, I can measure that on a tabletop. So because we use mercury and barometers, we need to be comfortable with working with that unit. Okay, so the one conversion, all the other pressure conversions will be given to you, but the one conversion that I want you to know for pressure is that 1 atmosphere of pressure is equal to 760 millimeters of mercury, okay, which is what's shown in these first two bullet points here. 1 atmosphere is equal to 760 millimeters of mercury. Know that conversion because it's very useful in dimensional analysis. Okay, 1 ATM is also equal to 760 torr. It's also equal to 101,000 pascals, or 101.3 kilopascals. Right? That conversion would be given to you, but know the one up top. 1 ATM is equal to 760 millimeters of mercury. That allows us to work between units. So That's a barometer. How about a manometer? Now, a manometer is something that is similar to a barometer, except it's now dealing with a closed system instead of a barometer that's open up top to the atmosphere. Okay, a manometer's got a closed system because we use it to measure the pressure of a trapped gas. Yeah, and we again use mercury. So let's see what those look like, because there's two types. There's a closed end and an open end manometer. Okay. With these closed ends, if it's closed at the top, I just have to use the height difference to see what the pressure of the gas is. Okay, because the pressure of the gas pushes down, forces the mercury up. Whatever the reading here is equal to the pressure. Okay. But these open ends, I have to compare the atmospheric pressure as well. Because notice there's a chance where the atmospheric pressure, which is typically 760 millimeters of mercury, can be pushing down and the column can end up higher on the left. Or if the pressure of the gas is high, right, then it pushes it up further to the right. And I look at the difference in height to get those new pressure readings. You'll have a couple of these on your sapling to practice. Let's take this one, for example. Okay. How do I calculate the pressure of the gas? Well, I see the height difference here is 26.4 centimeters. Okay. I convert that to 264 millimeters of mercury, right? That's the difference. That corresponds to the pressure of the gas in a closed end manometer. If this were an open end manometer, I would take that 264 and add it to 760, okay, because the pressure is higher over here, meaning it's pushing up against the atmosphere. 264 plus 760 would be 1,024 millimeters of mercury. So that's a lot of ideas about pressure in this video. In our next series here, we will start to talk about deriving the ideal gas law.